So on your notes, you should have notes that look like this. We're going to talk about these orbitals. And we're going to be talking about different bond types. So when we're doing bonds, the first bond in any situation is always going to be a sigma bond. And this is the abbreviation for sigma. This is a lowercase sigma in the Greek alphabet. Okay. So if we had, for example, ozone looks like this. I'm not done drawing it yet. Hold on. So this is what ozone looks like. The sigma bonds are the ones that are in red, and anything beyond a sigma is called a pi bond. So this would be a pi bond. Okay. If we were looking at like CO2, so carbon dioxide, this is the structure of carbon dioxide. How many sigma bonds do we have in carbon dioxide? How many pi bonds? Two. Okay. Now, when we're talking about in terms of strength of these bonds, a sigma bond is stronger than a pi bond. But a sigma and a pi are stronger than just a sigma. You can't have a pi bond without having a sigma there already. I know it's a sigma. I don't know why that's so funny. I don't understand that. I know I'm old, but it's just weird. Yeah. All right. So bond order, we've already touched on that quite a bit, trying to figure out what our bond order. So for example, the bond order is what for ozone?
1. 3 divided by 3. 2. Just kidding.
3 divided by 2 is what?
Something.
1.5.
Right.
Okay. What's the bond order for this one?
3 divided by 4.
No. 4 divided by 2.
Wait, what?
4. 1, 2, 3, 4. Divided by 2 bond sites. So the bond order is what? 2.
So why is that one not?
This one?
Yeah.
Because it has 3 bonds. This is 3 oxygens. This is an oxygen, a carbon, and an oxygen.
Oh.
This is carbon dioxide. This is ozone. So the bond order here is 1.5. The bond order here is 2. Which bonds are stronger? This bond here or this bond here? Ozone, the oxygen-oxygen bond, or the oxygen-carbon bond?
Oxygen-carbon.
Right, this is stronger, yeah?
Yeah.
Because the bond order here is 2. The bond order here is only 1.5. In reality, this is a 1.5 bond. This is a 1.5 bond. It's not really a 1 and a 2. Because resonance would exist here. We could draw this guy with the double bond being over here. Questions on that?
No, I just don't get how to do bond order.
So number of bonds, 1, 2, 3. I got 3 bonds there, right? How many places are bonded?
2.
So 3 divided by 2 is
1.5.
Okay.
Oh, so this one is 4 divided by 2?
This one is 4 divided by 2, which is
got it.
2. The more bonds you have, the shorter the bond. So the double bonds are going to be shorter than a single bond. So if you had, for example, fluorine, oxygen, and nitrogen, which would be the shortest bonds here? Nitrogen. Which would be the strongest bonds? Nitrogen. How many sigma bonds would nitrogen have? How many sigma? How many sigma? 1. The first one is a sigma. The subsequent ones are pi. So this is a sigma. These two are pi.
Is the first one always going to be sigma?
First one is always a single bond, or a sigma. First one is always a sigma bond. Sigma pi. Sigma pi pi.
Got it.
What is my bond order here?
4 to 3.
Which is,
1.33.
yep. Okay. Is this bond longer than this bond? No, they're both the same. Their bond orders are all the same. They're 1.3. It's kind of a trick of your eye. Like you gotta override that tendency. How many sigma bonds are in this molecule?
3.
How many pi bonds?
1. Pretty good at sigma.
Yep. All right. Now, we have talked about bond polarity, and bond polarity comes down to electronegativity. Okay. I think, again, you guys are getting fairly comfortable with that. You practiced some more yesterday with your Khan Academy. Okay. Give me an example of something you're struggling with then.
Nothing. When does the Khan Academy do?
This morning.
Right.
So I can extend.
Just turn it in. Okay. So which side of this would be negative? The fluorine end would be negative. Because remember, this goes back to electronegativity. Fluorine is the most electronegative on the periodic table. So this end of this molecule would be negative. This end would be positive. What that means is the electrons are going to stay on this side more than this side. Fluorine is an electron hog. Even though there's a sharing of electrons, that electron is going to be around the fluorine more than it's going to be around the hydrogen. So that's going to give this side a negative charge and this side a positive charge. Okay. So when we're looking at stuff like oxygen, which end of this is negative, which end is positive?
I don't really know.
Right here.
I don't know. Is it the same?
What does it come down to? What do you have to do to figure out bond negative, polarity? Electronegativity.
I don't know. Sigma.
Configuration.
Yeah.
No.
I wish I could say I understand.
Hang on.
Oh.
Oh.
A.
Room. House.
B. Post.
E.
What?
E. Perfect. N.
I thought there was an L.
Resonance. Something resonance.
BB at the beginning of the resonance.
You know what, Tony?
About
Is it
L.
like the
L.
long bonds?
Hell is a shit. Yeah.
Don't worry, bro. You're saying.
Okay, shut up.
I do have a pigmentation.
Wait. It's fantastic.
Mommy, don't think it was.
Why daddy will have me?
You want me to guess again?
Yeah.
N. Oh wait, no, not N.
Already guessed that.
My
Dumb.
bad.
A, B, C, D, E.
A, E, I.
That was good.
A, F,
G.
Wait, A, B, C, D,
come on.
E, F, G, H.
A, E, I.
Oh, F. D.
Differential. I don't know.
Oh, different.
Electron difference.
Different.
Electronegative difference.
So what's the electronegativity difference with this?
That's it.
Nothing.
Right. So this is not going to be a polar bond. It's not going to be a polar molecule because there's no electronegativity
Now ain't that
difference.
something?
That was a good game.
Okay. So there's no difference there. Now, the way we can show those differences with one side of the molecule or the other is we can draw an arrow towards the negative end and make the back part of the arrow a plus sign. Or we can use these Greek symbols with a plus and minus to indicate the positive end and the negative end. Now, we've talked about bond polarity, but there's also the polarity of the overall molecule. So overall polarity. So that's what we need to look at now to see if a molecule is actually going to be polar or not. And you can have molecules where you have polar bonds like this one, okay? This is going to be polar bonds between the carbon and the oxygen. So you can have a polar bond, but because this thing is symmetrical, those polar bonds balance each other out, and the whole thing overall ends up being nonpolar. Yep. So we talked about dipoles, right? What's a di means what? Two poles. Okay. Here you have a positive end and a negative end. But over here, you would have the positive and the negative, and it all balances out. It cancels those dipoles out, and you end up with a nonpolar molecule. So that's one thing that can happen. Another thing that can happen is, and this is a dead giveaway to if you have a polar molecule or not, okay? If you have lone pairs of electrons on that central atom, it is polar. You don't need to think any further. You don't need to give it any more consideration beyond that. If there are lone pairs of electrons on the central atom, it is polar. Write polar down and walk away. You don't need to think any further. All right.
Wait, so if on the first one, if it was like carbon and oxygen, would it be polar then?
So if it was this, yeah, then that would be a polar molecule because this is going to be, you're going to have a big electronegativity difference between those two. So that would be carbon monoxide. I'd have to figure out the structure of it. I'm guessing there's like a double bond in there or something. So I think this is the structure for that. 6 and 4 is 10, 2, 4, 6, 8, 10. Yeah, this is carbon monoxide here. Okay. But because there's a significant electronegativity difference between those two, this is going to be your negative end and this will be your positive end. And again, we can show that with an arrow where we have the tail of the arrow with a plus sign, and this is pointing towards the negative end. All right. The next one is ICl2. So this is going to be 21, 22 electrons for this guy. So we're going to start building him. We've got our iodine. We have our chlorine over here and our chlorine over here. All right. I have 4, 6, 8, 10, 12, 14, 16. Then I'm going to have to do 18, 20, and 22. So what is my geometry here? We got to go back to our chart from yesterday or 2 days ago. Can you find 3 lone pairs of electrons and 2 atoms? So we've got 2 and 3. Okay, it says it's linear. And it says that it's 180, I assume. Okay. And then if we were to talk about polarity, is this going to be a polar molecule? Why? Right. This one should be an easy one. Like everybody should get this correct. If they've got the structure drawn correctly, you should get this one correct like that. You don't have to think about it. You see these lone pairs of electrons on that central atom, polar. Boom. Done. Drop the mic, walk away. You are done. So this is polar. How many sigma bonds?
2.
How many pi bonds?
None.
None. What is my bond order? 1. So we've got 2 divided by 2 bond sites is 1. All right. This is 12. This is going to be 4 times 7 is 28, I believe. Check my brain fog today. I've got my oxygen here. I've got fluorines coming off here. If you are helping regular chem out, they're getting ready to go into Lewis dot structures in the next couple days. They do not do expanded octets. They know nothing about them. And they're not doing the boron, which is the reduced octet either. So don't try to, if you're helping them, don't try to confuse them with that. So they don't know what it is. All right. So I've got how many electrons placed so far? 10. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. And what do I got to do?
Bond it.
Yep, I'm going to double bond it here. All right. So that's going to take care. Oh, I don't need brackets. Sorry. I should have square brackets around the previous one, but not around this one. All right. So now what is my, is this going to be polar?
Yeah.
Yes, because the fluorine has a big enough electronegativity difference than the oxygen. So this is going to be a polar molecule. And we have 5 things coming off of here. We're going to have to figure out what that is. Look that up on the list. I've got 5 and 0. Trigonal, bipyramidal, and then what is my bond angle?
120 and a plane 90 perpendicular.
Okay, so what's happening with this, if you're wondering what's going on here, okay, is if we were to actually draw this, okay, you would have your central atom here and you would have 3 things coming out of it this way, okay, and then you would have one on top and one on bottom coming this way. So it's going to end up like that. So that's what they mean by 90. It's going to be 120 this direction and 90 going these other directions. So again, it's something that you're having to visualize in 3 dimensions that I'm drawing in a 2-dimensional space. So you would have 3 coming out this way. You would have 1 coming toward you and then 1 pushing back into the screen here. Does that give you an idea? You understand it? Okay. So that's why they're giving you 2 different sets of angles here. Tomorrow on your quiz, you're going to get that chart that I gave you. So you don't have to have it memorized. You just need to know how to use it. All right. We're going to draw the Lewis structures for these. We're not doing anything with hybridization, so don't worry about that. And then we'll talk about sigma and pi. 5, 6, 6 and 4 is 10. This is cyanide. It has a negative charge. Polar or nonpolar? Polar. We have a big enough electronegativity difference between these that it's going to make it polar. And sigma bonds. How many sigma?
One.
How many pi?
Two.
2. Okay, I think that's all we need to talk about on that one. On the next one here, we got carbon here. How many electrons? So 4 and 6 is 10, 12. Hydrogen, oxygen, 6, 10. Did I just have 12? How many did I have? I had 12. 2, 4, 6, 8, 10. And I'm going to have to double bond it. There we go. All right. Polar, nonpolar. Electronegativity difference between oxygens and hydrogens. Oxygen is 3,5. Hydrogen is 2,1. Yep, this is going to be polar because it's a 1.4 difference. So this is definitely going to be a polar molecule. And how many sigma bonds?
3.
3. And how many pi bonds? 1. Bond order?
4 divided by 3. 1.5.
Yeah. Yeah. Okay. So then the next one is ammonia. Polar or nonpolar? Polar. And this should be just a boom, you got it. Because you see these lone pairs of electrons on this central atom, it is polar all day. You got it. Okay. Molecular shape.
Where's your feet?
T-shaped.
Try again. Trigonal pyramidal.
Oh, my bad.
Okay. And we're not going to cancel out. It's actually going to have a negative charge going towards the nitrogen. This will be our positive end with the hydrogens. Number of sigma bonds.
3.
Number of pi bonds. None. Okay.
Wait, what was the little arrow thing about?
Yeah, I don't get it.
This shows you the direction of the negative and positive charges. So the negative end is going to be the end with the lone pairs of electrons. So you draw an arrow. The tail of the arrow is at the end where it's positive, and you make a positive symbol out of the end of that arrow. And the point of the arrow points to the end that's going to be negative. The other way, instead of writing it like that you can do is you can do this symbol, which is a Greek symbol, and put a negative at the negative end and that same symbol at the other end and put a positive by it. Yep.
Does it have to be that hydrogen?
No. And in fact, if you really wanted to get technical about it, it would be all of them. I just tried to find the middle and went from there. All right.
Okay, this is about Leah's praying over here.
What's wrong? What don't you understand, honey?
I just remembered that there's like
She remembers,
science in college.
she remembers that she has to take chemistry in college.
You don't have to take chemistry. There's other sciences you can take. If you're not majoring in like a science. Are you going into like nursing or something? If you're going into nursing, you got a lot of chemistry ahead of you, honey.
Yeah.
All right. We're looking at this bond here because they're talking about carbon-carbon bond. Which one of these would have the highest bond order? Ethane or ethene?
I think.
Huh?
I think.
Ene.
Okay.
This is going to be the highest bond. Its bond order is going to be 2, right? Because we're just talking about the carbon. This bond right here, we got 2 bonds over one site. Here we got 1 bond over one site. So this is going to be the ethene. And then which one would have the lowest bond energy? Which one of these would have less energy? Ethane, yep.
Why?
Because a single bond is going to have less energy than a double bond.
Got it.
Think about if you were trying to break like 1 stick versus 2 sticks of the same size. It's going to be a lot harder to break the 2 sticks, right?
Yeah.
You have to put more energy into it. Or take 2 pencils. All right, we're going to draw ethylene here. And I'm going to draw carbon dioxide again for you. All right, we're predicting the molecular geometries for the bond angles for each molecule. So we're looking at the bond angle here in the middle. What is the bond angle here going to be for these 2 carbons?
180.
180, yep. And that's going to be linear. These are both linear. And they're both going to be 180. How many sigma bonds do I have in this ethylene? Oh, wait a minute. Hold on. I didn't draw this right. Okay, now I drew it right. How many sigma bonds in this guy? 3. 1, 2, 3. How many pi bonds in this? 2. How many sigma bonds here?
2.
How many pi bonds? 2. Okay. All right. Now, we're not doing anything with hybridization this year. Don't worry about that. It's not that bad when you get to AP. It's just one little extra thing. You'll be fine. Get to AP. We'll talk about it there.
What's this big old guy?
No. What? Yeah, I don't know what it's called.
What's this big old guy?
All right. So when we're looking at this right here, okay, we're not going to do number 1. We're just going to look at this and we're going to figure out the bond angles. They're just talking about this 1 carbon right here. So we're ignoring all the rest of this stuff except what I've got circled. So what is the bond angle for this particular carbon right here that I've got circled? 109.5, because this is a tetrahedral. Okay. Remember, we've got a 3-dimensional object in a 2-dimensional world. You've got to override that 2-dimensional kind of gut instinct and use your chart. Okay. It's kind of like my kid, the pilot, right? They have to learn to fly just using their instruments so that when they're flying through clouds, they're not trusting what their body's telling them, because that's how you flip your planes around and stuff. Okay. They have to learn to override all of their body's instincts of what's up and down and trust their instruments. Huh?
That's a theory.
I don't know what.
Like, yes.
Oh, okay. I can't hear. My ears are all
What'd you say
plugged
the
up.
one was?
Huh?
195?
What?
What'd you say the angle was?
109.5.
It's okay, Libby. I can teach.
Yeah, teach her about sigma.
How many sigma bonds are in here?
4.
4. How many pi? 0. Okay. All right.
Still be big though.
So now I'm going to look at this guy right here. And I'm just looking at the stuff coming off of that particular carbon. So I'm focused in on this section of the molecule. What is my bond angle for this carbon? 120. Yeah. This is trigonal planar. 3 atoms coming off, no lone pairs of electrons. How many sigma in this section? How many pi? 1.
Oh, is that a still dressing?
All right, now we're going to look at, they wanted us to look at this carbon right here. Okay, so we're looking at the stuff directly coming off of that carbon. Yep, this is 180. This is linear. How many sigma bonds in just this section?
Two.
How many pi bonds?
Two.
All right. Now they want us to come down here. We're going to count the total sigma in this whole thing. So how many sigma here? 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 sigma. And how many pi do I have? 1, 2, 3. Got 3 pi's. All right. So you are going to finish the rest of this, but I'm going to make one change to your homework. So you're going to find number 2 here, and you're going to get rid of the last part of this, and you're going to replace it with indicate the number of sigma bonds and pi bonds. What?
Oh, nothing.
You good?
Said I'm hooked.
Once you get them drawn up here, you're going to reuse them for these 2 sections down here. So it seems like a lot, but it's really not once you get them drawn in the first part. Okay? So do sigma and pi. Sigma, pi. And you can continue that on. I do have the answer key
Is there
loaded
alpha
for
bonds too?
this. What?
Is there alpha bonds?
No, just sigma and pi.
So there's no beta.
For us, sigma is.
Yeah.
Was that a good quote?
Yeah, that was
No.
that was neat.
All right. So there you go.
Oh, I forget.
Mm.